Okay, here's the first full video with the new camera, and I've ordered a microphone for it, so that'll probably make the sound better, because when I did a test it wasn't so great. And here we go. We're now working on vector and matrix equations. This is video 2 to be watched today, the 26th, and a lot of this is maybe review, but we'll see. So let's jump right into it. Here we go. Start with a definition. A column vector is just an n×1 matrix. So all these years you've been working with vectors, you've actually been doing matrix algebra. It's just a very specific kind. So in R2, a vector u in column form would be u1, comma u2. In R3, it would be u1, u2, u3, dot, dot, dot. And in Rn, n space, it would be u1 down to un. Okay. So so now here's a big important definition that comes up all semester long. It's one of our standard language pieces. So we start with a set of vectors v1 down to vp in Rn. And it must be the case that p is less than or equal to n, otherwise this makes no sense. And we also have a set of coefficients in R. These are just constants. And the conclusion is then the vector y, which is c1 times vector v1 plus cp times vector vp, is called a linear combination of the vectors v1 down to vp with weights c1 down to cp. So this is a definition of a linear combination. It's just constants times vectors added together. And so here we're going to jump into some examples where we talk about how linear combinations work. Okay, we're going to let the vector a1 be 1 minus 2 minus 5. So we're working in R3. A2 is going to be the vector 2, 5, 6. And we're going to let B be the vector 7, 4, minus 3. Okay, so we have these three vectors in R3. So if we wanted to, we could put this on a graph and look at these. And the question is this, and we ask this question a lot: is B a linear combination of A1 and A2? Okay. So in other words, do there exist constants C1 and C2 such that C1A1 plus C2A2 equals B? Okay. Okay, so part of the reason I like using the GoPro is that it gives me more space to work. My only fear is that when I get this thing on YouTube, that the text is so small you can't read it. So we'll figure this out today. By the end of the week it'll be perfect. Alright, so let's rewrite this. So now we're going to take C1 times the vector 1 minus 2 minus 5, add it to C2 times the vector 2, 5, 6, and set this equal to 7, 4, minus 3. Okay? Just doing a little bit of matrix work here on the left-hand side, sorry, vector work. If I put this into one vector, I have C1 plus 2C2 on the left, minus 2C1 plus 5C2, minus 5C1 plus 6C2. This guy equals 7, this one equals 4, and this one equals minus 3. And so what do we have here? System of linear equations. And we know how to solve that. Stuff this thing into an augmented matrix and solve it. So let's do that now. So we go 1, 2, 7 from the first row, minus 2, 5, 4, minus 5, 6, minus 3. All right. It's an augmented matrix. Then we do some magic row reduced echelon form stuff here. We wind up with 1, 0, 3, 0, 1, 2, 0, 0, 0. And this first row says that C1 equals 3 and C2 equals 2. Okay. I skipped all these steps. All right, so to answer our question from above, is B a linear combination of A1 and A2? The answer, yes. If you take 3 times 1 minus 2, 5, and add it to 2 times 2, 5, 6, you get what? 4 plus 3 is 7, minus 6 plus 10 is 4, and minus 15 plus 12 is minus 3, which is B. Right. Okay. So let me check my camera here. I think it still should be showing. All right. Carrying on. Now we're really getting into it. This is key because I wrote it that way. All right. Again, let that same vectors. Let V1 down to VP be vectors in Rn. If I take the set of all linear combinations of V1 down to VP, the set of all linear combinations of the V1 down to VP is called the span of V1 down to VP. Okay, and we write it like this. We go span, curly bracket, V1 down to VP. Okay, and so note a vector B is in the span of V1 down to VP if and only if there exist weights C1, Chihuahua, C1 down to CP such that C1 V1 plus CP VP equals B. Okay, and this is, I'm going to put this in red. This is something we do all term, and there's lots of ways to get at this. We're taking it slow, and we're going to get there. But this idea of when is something in the span of a set of vectors, when isn't it, is crucial, paramount to this course. So if we go back to that last example I had, come on, Pullman. Let's see here. Yep, you can see that. 3. Okay. Rewording it using this idea, it's saying something like is B in the span of A1 and A2? And we answered this yes, and we found the C1 and C2 that made that true. Okay, so let's now talk about matrix equations, not just vectors. All right, so here we go. This is a theorem. The wording is a little hard, but a couple of examples I think will make it pretty clear. And after a month or so, not even a month, a couple weeks from now, it even gets clearer. So we start with a matrix. Let A be an m by n matrix. The majority of the course, m equals n, but for now we have to get through this. So let A be an n by n matrix. The columns of A are vectors, right? A1 down to AN. Let B be a vector in Rm. Then the matrix equation AX